Good morning, everyone. Welcome to the 2014 Next Virtual Workshop. Believe it or not, you're all part of this workshop that is going to go on for multiple months here. Here we have, today we have Professor Ed Maurer from Santa Clara University to talk about water resources, climate, and downscaling. And I think this is going to be a really interesting presentation because it really fits well with the workshop goals, trying to create climate resilience using Earth observations. Okay, Ed, I would call you Ed, has been in the field of hydrology. Though trained as a civil engineer, he did most of his work in hydrology at the large scales, climate and hydrology at the regional scales, actually. So it's in a lot of ways in line with what we do at NASA, more of a regional scales. And his work spanned modeling water and energy fluxes to seasonal forecasting of water resources and on to climate and climate change impacts on water resources. I think what Ed is most known for is his work on downscaling, which is still today is the gold standard for downscaling global climate models and for impact assessments. I think if you Google climate impact assessment, probably Ed would show up at the top of the list. I think beyond his work, and Ed is also actually quite of a role model, and by that I mean Ed teaches about 6 classes at Santa Clara University, which is a full load. And believe it or not, last year he published 17 papers. And I'm not sure how he does it, but that's, to me, that's a role model for anybody that wants to get into academia. With that introduction, I would like to invite Professor Maurer to give us the lecture on climate, water resources, and downscaling.
Ready? Yeah, go ahead. Okay. Well, thank you, Rama. That was a kind introduction. I'm happy to be invited to be a part of this. What I'm going to do is just scroll through some slides showing some of the work I've done over the past, especially 10 or 12 years. I've actually been involved in climate change work for much longer. So I am trained as a civil engineer. My specialty is water resources in a broad sense. I've worked in a lot of different areas of water resources. And as part of my dissertation work in the late 90s and early 2000s, I worked on looking at large-scale predictability, seasonal forecasting, things like that. About 10 or 12 years ago, I decided I'd take a look at climate change. I thought, well, this is not going to be that different, and thought I could just sort of stroll into this and find a way to take climate change projections and put them into a hydrology model and start to examine changes in hydrology as a result of climate change. And this has led to a very long path with a lot of scientific questions that really stretched me into new directions. That has been a lot of fun. So what I show here is, this is an old slide I've used for years. I borrowed it from other people. But it shows nicely the kind of cascade of models that are involved. Ultimately, this is kind of my domain down here. I'm interested in river basin hydrology, really, for the most part. And it's driven by processes at fairly small scales. But when you start to look at climate change, there are a few things that need maybe a little bit of explanation. As I start this process, you always have to start this looking at greenhouse gas emissions. So we're making some assumptions about what the future atmosphere is going to look like. Well, we don't know, so there are uncertainty bars associated with that. We make assumptions about what it might look like. The global climate models are things that we use, or I don't use them, other people use them, to look at how the Earth system will respond to different atmospheric concentrations of various greenhouse gases and changes in other properties of the Earth's surface. These produce output that then you can start to look at using for a hydrology model, but the problem is you've got the scale mismatch. Climate models typically run at spatial scales of 100 kilometers up to 500 kilometers in some cases. So there's this magical property or process called downscaling that we use to translate what the climate models output to something that's usable for hydrology models or other impacts models. So for the first two steps, climate model output is something I just obtained from a variety of sources initially, but most recently, or especially over the last 6 years or 7 years, it's all at one common archive. So what you end up doing is you have to make some assumptions about what the future climate looks like. Now there are these different pathways into the future that are built on assumptions. Here it's through the 21st century about how societies will develop, how interconnected economies will be, how population growth will happen and where it will happen. And based on all that information, they come up with these trajectories of greenhouse gas concentrations in the atmosphere, radiative forcing, and ultimately global surface warming. There are higher pathways, of course, looking at higher population growth rates, especially different assumptions about how quickly sustainable technologies are adopted. Lower ones that make much more optimistic assumptions about how those things will develop. And there's always one down at the bottom looking at kind of a thought experiment. Well, what if we had held everything at the same atmospheric concentrations as in the year 2000? What would happen to warming? So you have to make some choices here. You can look at it as a pessimist or an optimist. I think we're going to end up on this pathway or that pathway. If you look very early on, they're all pretty much on top of each other. There's not a great difference. If you zoom in a lot, we're tracking at or above the highest of these, but it's still early in the game. If we take action quickly in the next 15 years, we could conceivably get onto one of these lower pathways. So the further into the future you look, the more important the choice of the pathway is. Then, of course, you need to choose a climate model. Now, one of the nice things that's happened is around 2006, 2007, there was this coupled model intercomparison project, phase 3, I guess, is the 3. And as part of that, climate modeling groups from around the world, and I've listed climate models and the locations of their groups here, submitted output from consistent experiments. Experiments including historical climate model runs and climate model runs along each of these pathways, and they're all archived at one location, so you can just go there and download it. So as part of my early work on this, I went and I chose 11 of these models. So I took historical output from 11 models, and then one higher emissions pathway and one lower emissions pathway. Now, because I spend so much time on the downscaling step, I'm going to talk about that for a couple of minutes here. That output is essentially raw climate model output. It's not very usable by a hydrology model. Now, as we know, the landscape from a hydrologist perspective might look like this. It's driving all the interesting processes, orographic effects on mountainsides and things like that. And a slice through a watershed might look something like that, going from mountains down to the sea. You can see all the processes that would be represented in a climate model. Tends to see the world more like this, and a cross-section through a watershed might look something like that. It works on a global scale, on a continental scale. When you start getting down to river basins, that's obviously not going to be very helpful. So the downscaling process attempts to bridge that. There's a lot of information in these graphs, and I can point you to a couple of resources here that describe this stuff in much more detail, especially Andy Wood, who kind of developed most of this method. He had an article in the Bulletin of the American Meteorological Society in 2006 and a couple of earlier papers that explain this in a lot of detail. But essentially what you do is you look at, for some historical period, you take a box at more or less the climate model scale out of your domain, and you look at, for each month, so January, February, March, all 12 months, you take the climate model simulation of something like temperature. And in this case, these are all temperatures. So we've got temperatures from 0 to 7 for January, from 4 to 13 degrees Celsius for April. And you accumulate these into a probability distribution. So you'll have 90% of the values at or below this level, and 50% at or below that level. You do that for the observations, which are the red curves, and you do that again for the climate model, which is the black dashed curve. And then what you do is you take your climate model projection and historical period, and you basically map from one to the other. If the climate model projects this value, you come across and you pick that value for the observations. And you do that for every month in the time series from whenever you begin, typically 1950 or earlier, through maybe the end of the 21st century. And that's the process that's kind of described by this graphic. So obviously there are a lot of assumptions built into that. Most fundamentally is that this bias between the climate model and the observations stays constant into the future. So that was obviously a question people ask. And so I did one experiment looking at that. Other people have done similar experiments. What I show here is one GCM. I looked at one GCM, one variable, and here I'm looking at maximum daily temperatures. And I looked at two different historic periods and compared the climate model to observations. And what I show here is the bias. Again, this axis is the same as on the prior thing. So that's the cumulative probability. So these would be extreme high temperatures and extreme low values of maximum daily temperature. The green bar is the bias for one period. The red bar is the bias for the other. And you can see, choosing between two different historic periods, you can get very different biases. Choosing between two different levels of high or low values, you can get different biases. So that sort of could be a concern, knowing that that those are constant as a foundational assumption for this method. What I did was I developed this index. I named it the R index for lack of anything else. And what it does is it compares how big the change in bias is, or the variability in the bias between different periods, to the overall GCM bias. So where this R index has a large value, which in this plot would be kind of red colors, that those are areas where the change in bias is actually comparable to the original climate model bias. And what that means is that doing bias correction with this method may actually make things worse. Now this is just for one climate model. So you'll see there are a couple of cells where the bias correction using this method may actually deteriorate the value that you're trying to bias correct. But in most cases, it makes it better. And in many cases, it makes it much better. If you look at another climate model, it ends up, there will be, again, a handful of red squares, but they'll be in different locations. So as long as you use a set of several climate models, overall, the method works well. And another issue that came up is that people started noticing after doing this bias correction, some of the trends changed. And trends are, of course, what we're interested in with climate change. So if that's happening, we want to know, is that a bad thing? Is it a good thing? Is it something we want to avoid? One of the examples of this is shown here. I show mean annual precipitation between the middle of the 21st century and kind of late 20th century. Red areas are getting drier, blue areas are getting wetter. And you'll see before the bias correction and after the bias correction, they look very similar. But you do see some areas that here it looks wetter, here it's kind of in between wetter and drier. So there are some changes in trends. They're subtle, but in some areas it can be very important. Small changes in precipitation can be important. So what I did was, again, yes?
Can we go back to the previous slide? Because I think this is really critical. So here you used one model here.
Correct.
One model, one variable.
Yes.
So if we want to create those blue boxes, that's our goal, isn't it? The bias correction, to have as many blue boxes as possible.
Yes. Yeah, you'd want to see as many blue boxes as possible. But what happens is, for some models, there's a change in their bias between different periods in the historical record. And what that means is you can expect to see those kinds of changes probably into the future as well. And again, I did this for 4 different models, and when you look at them, the problematic cells, the problematic locations change for each model. So as long as you're using multiple models, you're far more likely to see a benefit from the bias correction than a deterioration of the signal. But it does emphasize that if you're doing a climate change projection with 1 model or 2 models, you may use, especially if you're only looking at 1 location, you may end up deteriorating your signal by doing a bias correction. You have to be aware that this sort of thing can happen.
So, are you planning on doing this for multiple models?
This was, I published this in a paper in 2013. I think I used a total of 4 models for this study. They were 4 models we were using in California for other studies. And I don't have any plans to go back and do it again with 10 or 12, but it could be done.
Yeah. So, Mila, this is something that we need to pay attention. Yes.
Okay.
Thanks.
Sure. So looking at the trend detection, the changes in trends that can be caused by this, and it's a known property that if your climate model tends to underpredict variance relative to the observations, it will tend to amplify trends after you put it through a quantile mapping bias correction. And you can flip that around as well. So what happens is I ran this through 11 different models to test it, and what I found was that, well, first let me show you this. I came up with a different index. I can't remember what I called it. I think it's a TM index for trend modification. Red areas on this map and this map are areas where, on average, you are making the trend further from observations than you'd like. And the blue areas are areas that the trend is actually modified in a way that's beneficial. It makes it closer to observation. So this is, again, looking at changes in precipitation between 2 historical periods. So we've actually got observations for both. When I looked at, again, this is winter precipitation in the top row, summer precipitation in the bottom, and what I'm looking at is 25th percentile, so kind of lower values, and 75th percentile. And ultimately what I'm showing is these dark blue squares here are areas where the trend is actually improved. So yes, this quantile mapping bias correction improves the trend in these locations. In these locations, most models actually deteriorate the trend. So it's a mixed bag. In some cases it makes it better, in some cases it makes it worse. Again, on average, you're going to do all right. If you're working especially in the southwestern United States, this would indicate maybe you're going to want to preserve your GCM trends and do bias correction in a way that retains that, and there are methods set up to do that. What I then did was, now I've got downscaled data. I ran everything through that process. I had 11 models. I took 1 location after my hydrology model ran. I had stream flows for the Feather River, and I'm looking at the late 20th century. And what I show is, in the black line is late 20th century average monthly values, so January through December on both of these x-axes. This column is for the higher emissions pathway. This column is for the lower emissions pathway. What I show are precipitation trends for each different model, or projected precipitation for each model, again, relative to observations, which are the thick black line. And each of those dashed lines and colored lines are a different model projection that's been downscaled for this watershed. the thing to notice really, well, let's see, precipitation is here, temperature is here, stream flow is here, and then I've got snow water equivalent on the bottom row. The temperatures are always higher looking that far into the future. It doesn't matter which model you use, it doesn't matter whether you're looking at the lower or the higher emissions pathway, it's always warmer, and that's a given. Precipitation is a mixed bag. Some are higher, some are lower. And what that means is stream flow then has some interesting properties. If you look at winter stream flows here, so we're looking at kind of December, January, and February, winter stream flows in almost every projection are higher, regardless of whether the precipitation is higher or lower. And what that's showing is the reduction of the snowpack in those months. So it means we're seeing snow melt earlier, we're seeing more winter precipitation falling as rain instead of snow, and that drives peak stream flows in the winter that are much higher. And conversely, that leaves less runoff for the late spring, which is shown here, kind of May and June into July. Regardless of whether rainfall is predicted to go up or down, stream flows are projected to go down. So these sorts of hydrologic impacts then are something we can kind of count on, whether we're on a low emissions pathway or a high emissions pathway. So if I want to then take that and make it something that's usable for a decision maker, it has to be put into more of a risk context or a probabilistic context. What I show here is I just lumped everything together. I took all 22, put them together into one box and said they're all equally likely. Here's the historical snow water equivalent values, and so dark values are high. The lighter colors tend to go to 0. By the middle of the 21st century, on average, it looks like that. By the end of the 21st century, it looks like that. And if we pull out one grid cell from that and then draw up what it looks like in a probability sense, we've got, again, I've flopped my axes here, so I've got a probability here on this axis and a percent of snow loss here, going from a negative loss, or I'm sorry, oh, oops, I lost my, okay. What we can do is say we've got a 2/3 chance that the loss will be at least 40% by mid-century. So, and the second thing is 70%, there's a 2/3 chance that we'll see a 70% loss by the end of the century, based on this output. So this is an ensemble of 11 climate models. So that sort of attaches a probability to these things. This is starting to look like something then that civil engineers can work with, or other managers can work with. But again, we've made assumptions about emissions pathways, that either one is equally likely. We've given each climate model an equal weighting. And there are a lot of assumptions there we aren't really sure what to do with. But ultimately, did you? Yes.
As a civil engineer, 70% probability. What do they look for when you guys make decisions for like building dams, and what kinds of probabilities are you looking at?
And before you answer that, and since Rama's not mic'd, apparently our virtual audience can't hear the question, so if you could kind of rephrase the question for your answer.
Okay.
Yeah.
So.
And you know, what kind of probabilities are important for you guys? You know, like 30% versus 50% versus that. I mean, when you really choose to act on a piece of information.
That's a good question. So the question is aiming at what is the probability, or what's the chance of seeing these sorts of changes that will start to drive engineering and policy responses? And I don't have a really clear answer on that. I think it varies a lot depending on the system you're examining, how the cost analysis gets done. Ultimately, it comes down to kind of an economic analysis of risk and probability, or probability and impact, which gives you the risk. And so it ends up kind of being an integral across the whole space of the changes. So I'd have a hard time attaching a number to that. Yeah. So sorry, I don't have a more satisfactory answer for that.
It's okay, because now that is becoming important, in terms, so far people have said, oh, we're not really sure about these things. But now we are saying, there is, in this case, you're saying there is 70% probability that something like this can happen. So what does that mean if you're a practitioner?
Yeah, ultimately, I think for something like the Feather River, or wherever we're looking here at this one grid cell, knowing that there's a 2/3 chance of seeing a 70% loss of snow by the end of the century, by the end of this century, and that's throwing equally likely a very low emissions future in with a higher emissions future, that has already inspired some changes. And if you look at some policies, they're getting to the point where they can start putting numbers into policies. So you need to build levees to withstand a slightly greater depth of peak flow. You need to start, people have already been looking at operations of reservoirs in particular. You have this loss of snow. What it does is it changes the water management strategies throughout the year. So, and there are people looking at that. The adoption of specific policies to respond to these things is slower. Yeah. And a lot of that hinges on the fact that we're having trouble, as all of us, of attaching real probabilities to this. And actually that leads into the next thing that I'm showing here, which is kind of much more of the engineering approach to things. What this is it's a figure from a paper that Tapas Das was the first author on. He led this study looking at 50-year floods. Now, a 50-year flood is a flood you expect with a 2% probability in any given year. This was for not one particular river, but kind of a clump of the northern Sierra Nevada. He has a similar plot for the southern Sierra Nevada. And what it shows is the percent change in this 50-year flood. And the red line, again, is the higher emissions pathway. The blue line is the lower emissions pathway, and those are ensemble medians, and there are dashed lines showing the standard deviation around that. And what it shows is that regardless, again, about half the models are showing decreasing precipitation, half the models are showing increasing precipitation, but we're still seeing very robust increases in these peak flood events. And that has to do with superposition of snow melt and rainfall events and more intense rainstorms, things like that, that are well-known impacts of climate change. And these will greatly exceed what we'd expect from natural variability within our lifetime. So how this can get incorporated, one method was published in a paper in 2010 that was kind of showing how, if you want to design for something to be at, say, withstand a 100-year return level, but you want to do that, plan for a lifetime of that, whatever you're building, to be in service for 40 years, then for it, 40 years from now, to be designed for a 100-year lifespan, or withstand a 100-year return period event, you can develop a theoretical curve and then say, well, I need to design it for a 135-year or 130-year event in the present. So there are ways like that to kind of play with standard engineering analysis and stay within the framework that engineers are comfortable, but modify it to accommodate future projected changes. And some of that is already, the principles for that are already built into our manuals. This is the standard flood frequency analysis manual from 1981. And built right into that are confidence levels. So you don't just work through your numbers looking at historic stream flows and come out with 100-year or 50-year recurrence interval floods, which would be this is an example showing here's a 100-year flood, here's a 50-year flood, but you can put error bars around it. It turns out to get to this level, to accommodate that change in the 50-year flood, it's about the same as just designing for the upper 95% confidence level of that curve rather than the median. So there are methods that we can adapt current engineering practice to accommodate these sorts of changes. They haven't really been implemented yet, but I think we're getting closer to understanding how this can work. One of the nice things about this whole process is that it's very portable. That climate model output archive is global output, of course. The downscaling technique can be run on a PC. It's a very simple process to run. So I was able to pull this out and run it on the Rio Lempa Basin, which is mostly in El Salvador, but it covers some other countries in Central America, because I was interested, working with some people at the university in San Salvador, in the changes that might happen along the Rio Lempa, especially because it's such an important hydropower resource for them. And one of the things that we found from this, again, is that we're looking at a potential significant reduction in hydropower generation, a lot of that driven by changes in precipitation. And I, again, ran a very similar process down in Chile with some colleagues at the Catholic University in Santiago, and just show some output from that here. Here's the country, here's kind of what the Mataquito Basin looks like as far as its annual cycle of precipitation and stream flow. Again, very snowmelt driven, more intensely than in California. And then looking at the projected changes in different flood events, again, a 5-year event, 20-year, 50-year, and 100-year event, and found more or less comparable things that, especially for the high event, the longer return period, the more extreme events, we're seeing pretty significant increases in those amounts. And the greater the warming, the more those changes occur, the more intense those changes are. So I've spent a lot of time with downscaling, and I've shared a lot of my data with a lot of other people. And in the process of that, there's been kind of a crowdsourcing effort looking at different aspects of it. I showed you some of the investigations that have been done looking at some of the weaknesses and strengths and how they play out. And there are certain things, there are many other methods out there for downscaling, and they're becoming much more available. There are prepackaged software packages to run many of them that make it very accommodating. One of the methods I'm showing here is developed by Dave Pierce and Dan Cahan at Scripps Institution and sponsored by the California Energy Commission. And it's aimed at getting at especially combining the ability to downscale daily variability to get at extreme events and to correct for biases in models' long-term variability. So are they getting El Nino oscillations about right, that kind of thing. Those are especially important if you start to look at things like drought. This has been developed. They're processing a lot of data through it right now, and I think we'll start to see that. And intercomparing downscaling techniques is something that's becoming much more common, and something I've been at least peripherally involved in is a new effort through the CORDEX, Coordinated Regional Downscaling Experiment. About a year ago, they initiated an empirical statistical downscaling intercomparison project. So that's supposed to take all these different downscaling techniques that have been developed by people around the globe and compare them all among each other with standardized experiments and common databases. And that'll help us understand how they perform in different climates and in different locations, and for different metrics as well. And there are other projects as well around the world. So I've spent a lot of time with that stuff, but I also have probably seen much more interest in the downscale data that I've produced than I have in any of my other research. And what that did, I mean, the impacts that people are studying, anything from wildfires, heat waves, air pollution quality, air quality events, smog events, things like that, reservoir operations, crop yields, all kinds of different things. Some of the more far afield from my areas. Someone was looking at bumblebee emergence from Tuolumne Meadows and wanted to look at climate change impacts on that. So all kinds of things people are interested in. And one of the problems is they all need to develop downscaled data. And so I started sharing my data, but found it very inefficient to do so. And what happened was Levi Brecky at Reclamation, along with Tom Pruitt, who was kind of the technical point person for all this, we were able to put together an online database where all sorts of downscaled climate data could be served. This has been accessed thousands and thousands of times. Terabytes of data have been downloaded. And it's developed using exactly the same techniques as I had used, but uses 16 models in total and multiple runs for many of the models and 3 different emissions pathways here. So for a total of 112 different climate projections. And anyone can go to this website, check a bunch of boxes, and download that data. It's been used widely. This is from, I think, last September. We had, for some grid cells, as many as almost 14,000 downloads. So this shows the darker the red colors. The red colors tend to be areas that have been downloaded many, many times, thousands of times. Bluer areas maybe hundreds of times. And the asterisks show locations where people have downloaded these data. So it's widespread, and it's not just, it's around the world as well. People are still accessing it, even though the data are over the US. It's been used for research and management, planning, education, all kinds of different applications. But one of the things we didn't really get at with the original data set, that was all monthly data that we had downscaled. People are interested in things that really impact human society: heat waves, floods, things that happen at short time scales. And so what we wanted to do was expand the archive. So we looked at the daily GCM output as part of the CMIP3 project. It was limited. There were time slices, only certain models had it. But we were able to downscale some of that and add it to the archive, which is what I show here. So it's expanded to include a different method right here, the BCCA, which is a bias correction constructed analogs method that was again developed down at Scripps Institution of Oceanography. Hugo Hidalgo, Dan Kahan, Mike Dettinger put that together. We ran their code and developed downscale data for that as well. So it expanded what was available, although we found not nearly as many people used the daily data. It was additionally run through a hydrology model then, since it was daily data, and some hydrology output was also posted on the website. So you could go there and look at things like stream flow changes, snowpack changes. Only a portion of the United States was included in that, though. A lot of things were missing, and of course, as soon as you share anything, people ask for what you haven't shared yet. One of the things is the original climate model data was served in this format called Netcdf. It's a binary packaging that's very efficient with storage space. It contains the metadata and the data itself. It's probably the most common format for climate-related data. The problem is that most users of the data at kind of the engineering level or the policymaker level might not have the tools to really work with Netcdf files. In addition, you were able to download kind of rectangles from that website, but you couldn't bring up a watershed and just pull down a watershed. And also, as soon as I truncated the domain somewhere in northern Mexico, people wanted data in southern Mexico and other areas of the globe. So that was solved by a group kind of headed by Evan Gervetz, who was at the time at the Nature Conservancy. He's now at the University of Washington. And the Nature Conservancy allowed me to continue with the downscaling effort, and I did it for globally at a slightly coarser resolution, about 50-kilometer resolution, for I think 48 models in total, 48 model runs. And then those were uploaded to this online tool called the Climate Wizard. And what that does is it allows you to go on, select the particular models you want, the statistics, things like average temperature, average precipitation. You can then produce online graphics, online statistical analyses, download the graphics, download the data under the graphics. So it lets you do a lot of the processing there on that server and then download the final product rather than having to download it and work with it yourself. So that's shown itself to be pretty helpful. It also allows people to upload shapefiles. So if you have a particular domain you're interested in, you can clip that out of the global product and look at that. So especially for a first pass through an area, this becomes a very powerful tool to see what climate models are projecting. And this is one thing I looked at. I pulled down 16 models, 3 different emission scenarios, and this took maybe 15 minutes to plot how it changes. I think I truncated the axis here, but it's looking at, for each model, the change in temperature for this particular location, one latitude and longitude that I pulled off. And it puts a line across where the mean is. So it gives you an idea of what the mean projection is, what the variability is among models. You can limit it to certain models. You can look at certain emissions pathways, whatever you like. That's been subsequently expanded with some daily downscaling, with some work through the World Bank that has let us also add, through a spin-off website or a linked website, things like extreme precipitation or extreme warm days. And again, this is using data from CMIP3, so they're only slices into the future. But again, it's global, so that becomes very useful for other parts of the globe. You can look at how heat wave probabilities might change in certain areas. A lot of other variables are on here. You can, again, choose different models, different runs, different emission scenarios, or statistics related to consecutive dry days, number of heat wave days, things like that. So a lot of this data are out there now, and what happens is, as an impacts person, you may just be overwhelmed. You've got hundreds of projections into the future, different emission scenarios, different climate models, different downscaling methods. What do you use? A lot of times, especially if you're running a very sophisticated impacts model, you can't just say, well, I'll just take all 112 or 250 or whatever you can get, and I'll run them all through my impacts model. So what happens is people end up making choices, and here's one example of that from a report by Levi Brecky, where he was doing some work for reclamation in California. So this is above Folsom Reservoir. What he did was he took all the projections. So I think he's got 112 here. So this is 3 different emissions pathways. The precipitation change on this axis, the temperature change on this axis, and then he put the 10th and 90th percentiles along each axis and chose the climate model closest to the 4 vertices. So that gave him a way to only use 4 models, which then he can put through a much more sophisticated reservoir operation model and kind of span the variability. So you have a wetter model, a drier model, a warmer model, a cooler model. And that's one way you can do it. One of the problems with this approach is with only 4 models, we know that we can potentially be violating some of the things we'd like to avoid with the assumptions behind the bias correction. You're also introducing issues related to natural variability. So if you have a model that tends to produce a very long Pacific decadal oscillation or something like that, it may look like a trend when really it's just an oscillation in the model, and we do see that in some of the models. So what I show here is kind of a bigger look at that. Is there a way we can filter the models, take only the best climate models? And this was, again, from a paper, I was a co-author on this with Levi Brecky in 2008. And what it shows here are, again, cumulative distribution functions for climate projections. And what it's showing is, on this plot, just annual temperatures, how the projections change if we use no model filtering, so you get this gray line about here. So that's what you get if you just throw all the models in there. If you take only the best models related to water supply, you get these green boxes. If you take only the best models related to things important for flood control, you get this red curve. Now you see differences, but you don't see huge changes, especially when you're looking at impacts across the whole spectrum. And that was really what we found. Now these different sets of metrics, the water supply would include things like teleconnections between El Nino and land surface precipitation. There were, I think, 75 metrics in total. So a lot of different, different filters went into producing these. And you come up with more or less the same answer, whether you filter or not. Another report that I showed here shows each column is a different climate model, and each row represents a different land surface variable or atmospheric variable, total column water vapor, precipitation, cloud cover, and they're color-coded by skill. So the best are kind of the deeper blues and the worst are the deeper reds. So you'll see most models have some red and some blue in different proportions. But what you see over here is the ensemble mean and the ensemble median. And those leap out as the best among the bunch. And that's a pretty robust finding. You can try to just pick the best models, but as long as you average across a group of models, you're probably going to end up with a higher skill result. That's really become the standard for impacts analysis. Now, how many climate models? There was a nice study done by Dave Pierce in 2009, came up with answers in the area of maybe 10 to 14. That's maybe a good number to aim for. There are some more recent papers showing that model skill in producing certain variables in the historical record actually can correlate with improved projections, but that's only for specific variables in specific locations, and I don't know that that it's, the bottom line is, as long as you're including enough climate models, you don't really have to worry too much about their skill. If you're going to cull them, sure, pull out the worst models for whatever variable you're concerned with, but it's probably not going to change your answer substantially. One of the big questions I've been getting lately is, within the past couple of years, the couple model intercomparison project, fifth phase, has produced all of its output and made it available online. We've also run it through the same downscaling process, added it to the same interface we've got for all the other output, and what you'll see is many more models involved. And instead of 3 emissions pathway, there are actually 4. There are 3 that are comparable to the other 3 that we had in the older report, and then one much, much lower. That's, again, kind of a thought experiment as to what would be possible. So the question is, among people who are doing these sorts of impact studies, do we have to throw out everything we've done to this point and redo everything now that this new model output is out there? And really, to answer that question, what you need to do is take a look at uncertainty and think about this. Got a couple of slides I borrowed from Catherine Hayhoe, who did a very nice job of summarizing this. And uncertainty can be broadly categorized as natural uncertainty or natural variability. So the climate, we have warm periods and cool periods, and there's nothing we're going to do about reducing that. That's uncertainty we're stuck with in our process. But then there's uncertainty related to how the climate is going to respond or how well our models can simulate that. And that can be broadly called scientific uncertainty. And then the bottom is human uncertainty. We don't know which emissions pathway we're on. We don't know where we'll end up in 2100. So this you can't reduce. This, I don't know how you can reduce that and figure out which emissions pathway we'll be on. It depends on a lot of the things we do. But this piece, improved climate models could conceivably reduce that. And how important is that scientific uncertainty? What this graph shows is the contribution of these three types of uncertainty to total uncertainty or variability by the end of the 21st century compared to kind of the end of the 20th century for precipitation. And what you see is that the lion's share, 60, 70, 80% in some locations, the lion's share of this uncertainty is related to how the climate system is going to respond. Even for temperature, where what we do, the amount of carbon dioxide and other greenhouse gases that we emit to the atmosphere, that's a huge driver of variability. But you'll also see, over the poles especially, that, again, how the atmosphere responds is important. So how the models capture how the atmosphere is going to change, or how the land surface is going to change in response to these increasing greenhouse gases, is very important. So if we look at the climate models that are included in CMIP-5, we want to know how much better they do. And the first thing to just kind of step back and look is, are they really different? And what I show here is, this is right from the new IPCC 5th assessment report, came out last September. So they summarized the CMIP-3 models here and the CMIP-5 models here. And again, you see more models for CMIP-5 than CMIP-3, maybe a good thing. We see atmosphere, ocean, general circulation model or global climate model here. And the thing to notice is that darker colors in these columns for the atmosphere and the ocean indicate higher spatial resolutions. And compared to what you see here, there's much better spatial resolution there. And that's really important for being able to capture feedbacks over smaller areas. And there have been studies already showing that this improvement in spatial scale can produce better projections, more skillful projections. Another thing is the Earth system models, which are these kind of carbon cycle and other nitrogen cycle feedbacks that can occur within, or can be simulated or included in the structure of these models. The colors here show which of these models include different aspects of that. These are important feedbacks that can really change how your land surface and atmosphere respond to changing greenhouse gas concentrations. And if you look at the CMIP-3 models, they were virtually not there. And many of the models include those now. The last thing I'll point out is this little column here. You see a little FC here and another couple here. That's a flux correction. Some of these models tended to drift off into climatologies that didn't really look like the real world. And so they would nudge them back to reality periodically with these little flux corrections of momentum or mass or energy. And if you look at the CMIP-5 models, they don't use that anymore. And that's a real problem, because that all of a sudden, once you include that, you're not balancing your mass, you're not balancing energy, and it starts to raise other questions. So they look like the models are probably better in that sense. They include more processes. Ultimately, they're more diverse. So how do they perform? Again, this is from the same IPCC report. This is one graph that this piece of it got a lot of publicity last time. Again, this is the CMIP-3 ensemble. So each of these little traces is a different climate model. And this is CMIP-5 up here. The darker lines represent observations, and what's shown along the bottom is the period in months for different oscillations. So it's sort of showing the types of how strong the variability is at different frequencies. And this is important because this is for surface temperatures over the Nino 3.0 area. So it's looking at kind of whether these models get a realistic El Nino or any sort of El Nino. And you expect with the observations to see this come up and kind of peak in somewhere between 2 and 7 years and then drop off a little bit. And if you look at the CMIP-3 models, some spiked with these crazy powerful El Ninos, others kind of didn't have anything at all. There was a cluster of them toward the middle, so there was some hope there. When you look at CMIP-5, it's markedly better. There are still some that don't get much of an El Nino, and some get an El Nino that's much too strong, but you can really see an improvement there. And that's documented in these tables, that there are improvements. They're slight, but they're improvements. So if they're getting El Nino better, that drives a lot of climate impacts. That could be a positive thing. Justin Sheffield at Princeton has also done a very thorough couple of studies looking at how these models in the CMIP-5 ensemble perform across North America, looking at things like precipitation, winter precipitation and summer precipitation. CMIP-3 is here, CMIP-5 is here, again, CMIP-3 and CMIP-5. And what's on this axis is a measure of the error. So this black line is the multi-model mean, so the multi-model ensemble mean. And what you see is that it's about the same. You don't see huge improvements, but slight improvements for summer precipitation. An improvement here for winter temperatures, an improvement here for summer temperatures. It's an improvement or about the same for almost any of these metrics. Sea surface temperatures under the 2 for winter or summer. So again, it seems like by including more physical processes, a finer spatial resolution, not including a flux correction, all those things would work against you as far as climate models go. You'd expect to see more variability, and you're still seeing skill improvements. So that's a really positive thing. And finally, looking at the experiments that are done, there are more experiments. Now, this is kind of a complicated, there's a lot of information in this. You can look at Taylor's original paper from 2012, where he describes all these different experiments included in CMIP-5. What I was most focused on in the past were these historical model runs. They cover a longer period now. They go up through 2005, and actually many of these models have extended them into 2008 or even more recently. So that means we can get the last decade, especially, which wasn't available with the CMIP-3 runs. And there are still higher emissions pathway, lower emissions pathway, something in between. There are control runs, all the things we'd want. And they're done for longer periods. They're done continuously. They aren't done with time slices. So there's a benefit to how the experiments were structured. So as a bottom line, do we see any difference? Again, I'm showing temperatures on this side, precipitation on this side. I'll just look at precipitation for now. These are changes projected by the middle of the 21st century here for winter on this row, summer here, and by the end of the 21st century for winter and summer here. This column is for CMIP-3, the higher emissions pathway. This column is for CMIP-5, for the higher emissions pathway. The first thing you realize is they look, from a broad perspective, they look pretty similar. And that's a good thing. That would help us maybe say, maybe we don't have to redo things. They look almost the same. But if you're interested in, say, the headwaters of the Colorado River, it's slightly darker blue there than here. Well, that means instead of, as an ensemble mean, it being kind of half models wetter, half drier, here maybe there's a preponderance of wetter models. And what this is, it's the difference between these two, showing that we do indeed see wetter conditions under SRES, under the newer CMIP-5 higher emissions scenario. The thing that this starts to inspire is the thought that, well, in CMIP-5, they aren't really the same emissions pathways. Their high emissions pathway, the RCP 8.5, includes higher radiative forcing, a little bit more global warming than you expected under the higher emissions scenario, the A2 emissions scenario. So what happens if they're all just divided by carbon emissions, cumulative carbon emissions? And that was shown here, and again, it's part of the 5th assessment report from the IPCC. And it takes all the different emissions pathways and puts them as global temperature anomaly versus cumulative total atmospheric CO2 emissions. So how much warming do you expect per CO2 emissions? They all pretty much fall on a line. What that means is that there's the potential to scale these things and say, maybe let's not worry about whether we're on RCP 8.5 or RCP 6.0 or 4.5. Let's just say what's going to happen when we hit this level of cumulative carbon emitted to the atmosphere. And then the emissions pathway isn't that important. You sort of take time out of the equation. And that's sort of what was done here. Claudia Tabaldi and her co-worker or partner, I don't know, came out with a paper very recently looking at some of these scaling properties. And some of these types of plots were also included in the fifth assessment report. And again, temperature is shown here on the top row, precipitation on the bottom. We've got all the CMIP3, I guess 3 emissions pathways, 21 models, something like that. Similarly, for precipitation. For the fifth assessment, or the CMIP5 output, we've got same thing, all emissions pathways and models thrown in here and here. And then the difference between these two for temperature and for precipitation. And what they show is the change for precipitation in percent per degree Celsius of global warming. And here it's the change in local temperature per degree C of global warming. And of course, again, from a large picture, you look from far enough away, and these look the same. There's no marked difference between the CMIP3 and the CMIP5 output. Similarly with precipitation, these are the pattern correlations between the two, very high. It's within what you'd expect by natural variability, the difference between the two. When you look at specific cells, however, there are some places where differences appear, especially if you look at precipitation. Some of the northern latitudes, there are some locations where you see the stippling, where these are different. What that means is that these could be dynamical differences between the models included in CMIP5 and CMIP3. And you do see some of those over the western United States. So the differences that we're seeing between the CMIP3 and CMIP5 output over the western US, for example, they may be due to actually different dynamic responses being simulated by the models. So ultimately, when I have to give an answer for should you redo things for CMIP5, with the tools online, you can do a very quick analysis of how different they are for wherever you're looking, whatever statistic you're interested in, whatever region. You can grab a dozen models from here and a dozen models by the same modeling group even that participated in CMIP5 and compare the two. And if they do look very different, you might go back and do some trial runs, start to redo some of your work. The important thing, one of the important lessons that I've sort of learned is that going back to some of the old tech approaches to climate model impacts or climate impact studies, it's important to understand what system you're interested in and how it tends to respond to changes in precipitation or changes in temperature. So this is a standard sensitivity plot that was developed for one location in California, I believe, back in 1996. And then you can superimpose on something like this any changes from CMIP3, CMIP5, or even CMIP6, which is coming. And we're going to be faced with the same thing. Do we throw out everything from CMIP5 and adopt CMIP6? So understand your system, understand the sensitivity. So finally, where are we with this? I'd say as far as for my work, water-related impacts of climate change, a lot of things have improved. We understand downscaling more. We're seeing improvements in downscaling techniques that'll help to solve some of the shortcomings of current techniques. We understand how data can be used because of our experience distributing lots of data, and so we understand how we can provide more guidance to users. And people are understanding that Producing downscaled data isn't an end in itself. We have to really communicate with the people on the ground who are trying to work with vulnerabilities and risks and developing policies to respond to this. And how do we provide data to satisfy what they need? And that's an important piece that's now becoming much more common among people doing downscaling and modeling. So some of the things, some of the past work that we've done with CMIP3, we may need to look at again because some of the impacts will change. And one of the things that's happening is we're starting to realize differences between downscaling methods can produce a level of uncertainty in your projections that can be important, and maybe including more than one downscaling technique can also be a valuable thing to do to characterize your uncertainty for any projection. I think that's it.